じゃあ、good afternoon, everyone. Thank you very much for joining this I²CNER seminar series today. The I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. I am Yuichi Sugai, a member of multi-scale science and engineering for energy and environmental trust, and I will be your host today. Today, we welcome Professor Yasuhiro Yamada, a professor of Department of Earth Resources Engineering, Faculty of Engineering, Kyushu University. I'd like to introduce Professor Yamada briefly. He earned his PhD from Geology Department, the University of London, Royal Holloway in 1999. And he started his professional career in the oil and gas exploration industry as an exploration geologist, then moved to Kyoto University when he conducted research on geologic modeling, CCS, oil and gas related research, and scientific drilling. After spent 11.5 years in Kyoto, he moved to JAMSTEC, where he was leading the science to explore subsurface by combining various data sets, such as exploration, geophysics, borehole, and core data. From 2021, he is a professor at Kyushu University. Recently, he is now studying on natural hydrogen reservoirs. And today, we invited him as a lecturer of this seminar. So now, I would like to invite our director, Professor Tatsumi Ishihara, to begin our session.
Good afternoon, everybody. And my name is Ishihara, the director of this I²CNER. And first of all, Yamada Sensei, thank you very much. Accept today's very interesting talk. And usually we invited quite prestigious researchers visiting to Japan to invite it here. But today's topic is a little bit different since we have very strong interest on the green hydrogen, but another name of hydrogen recently become popular, which is white hydrogen. And I heard from the Sugai Sensei that the white hydrogen is very fortunately in Kyushu University, we have a very nice professors. Yeah, so that is why I asked to the Sugai Sensei to invite him. Therefore, I very looking forward his talk on the white hydrogen, what is ongoing. So first of all, thank you very much, Yamada Sensei, and I'm very looking forward to your talk. Thank you very much.
Thank you very much, Tatsumi Sensei. So before we begin, I would like to take a moment to remind you that your question will be addressed after the presentation. Zoom listeners, use raise hand button or type your question or comment in the Q&A box. Okay. When you are called on, please unmute yourself. So this webinar will be recorded and made available on the I²CNER website. So now, everyone, please welcome Professor Yamada.
Well, thank you very much for giving me such an excellent opportunity. And I'm Yasuhiro Yamada, and today's my topic about the natural hydrogen. Okay, well, since I've been working on I started my career from the oil and gas industry as an exploration geologist. So since then, I have been exploring subsurface in the past nearly 40 years or so. So in terms of oil and gas first, and then for the CCS and hydrate and other resources, and then extend to natural hydrogen research. in the past few years. So my basic background is such an exploration of the subsurface. Okay, well, this is the content of today's my talk. First of all, this natural hydrogen is white hydrogen, and this is a relatively new topic, maybe for many of you. So I'm going to introduce what this is. And then in order to find and produce the natural hydrogen from subsurface as an energy resource, we need to understand the system. So I'm going to explain what this is. And then also we need to understand the method to explore and produce natural hydrogen from subsurface. And recently, we have started a research project here in Kyushu. And so I'm going to introduce what the idea and what we are now doing at the end of my talk today. Okay, well, natural hydrogen, and this is, of course, that is produced in the nature because that is natural hydrogen. So, and this research and the activity by the academia and by the industry then has been booming in the past, say, 10 years or so. It's quite a new topic. And it's the attractiveness of this topic to the industry is that the cost can be extremely cheap to produce hydrogen and to compare other methods. And that's why, and this may be a strong merit for the natural hydrogen to explore and produce from subsurface. Okay, but this is still a kind of research stage at this moment. So where the commercial discovery is not established yet. So one producing field is a small one in Africa, Mali, and that is the hydrogen supplying for a remote village. So it's still small scale, but there are a number of drill holes by the company and also funded by the government as well. So that is now worldwide is getting more broader phase. So I'm going to explain what's going on here. Well, in the past, the major oil and gas companies started this natural hydrogen research and exploration in the past, say 20 years or so, but it hasn't disclosed yet. So it's still internal information, and then nothing has opened to the public. And in say less than 10 years or so, the US government decided to fund this natural hydrogen research and through the Department of Energy. And that funding goes to USGS, United States Geological Survey. And they have started natural hydrogen research. And they started the paper production and also the presentation at academic societies from 2022. So it's only 3 years ago. So since then, a number of papers are published, and the reports and published and science articles, and also BBC reported the mass media, and also Japanese JOGMEC has produced a report based on this. So this is new in the past few years topic. And then so yeah, as I said earlier, this is still research stage, and that's why the system of natural hydrogen is still unknown. So the many researchers are working on their field to establish their system of their area. I'm going to explain what this system means. Okay, well, the type of the hydrogen, as many of you know, that the hydrogen has been produced from natural gas, for example, and that is called gray hydrogen. And that has the environmental impact because the production of hydrogen from natural gas produces carbon dioxide as well. So that is emitted to the atmosphere. So that has an impact to the environment. So once that the carbon dioxide is captured and used for the industrial purpose or storage in the subsurface, and the hydrogen is called blue. So blue hydrogen. So that means because of that, the CCS and CCUS, the carbon and the environmental impact will be lower, but of course the cost will be higher. And if you can use the renewable energy resources, including biomass, then the hydrogen can be called green hydrogen. And of course, that is environmentally friendly, but the cost is much higher. So that kind of a discrepancy between the cost and environmental impacts. And the natural hydrogen merit is this is naturally occurring. So once we can find a commercial size of gas field in the subsurface, then of course the environmental impact will be low and the cost can be very cheap, like a natural gas field. And that's why many companies are working on to explore and find commercial size of natural hydrogen gas field in somewhere in the world. Yes, the cost estimate is still unknown, but some say that it can be just 1 kilo US dollar. So it's very cheap compared to others. Okay, so there's some example. It's not commercial discovery yet, but it's fairly well discovered of the sign of natural hydrogen in the subsurface. One example is from Australia. This is the York Peninsula area near Adelaide City. And the company has drilled several holes in this area already. And in the past, the shallow holes suggest the gas from these boreholes, mainly that is not natural hydrogen. So 80%, 90% of the gas from the shallow borehole has known that it's almost purely natural hydrogen. And then the company have drilled quite recently, and then they have discovered that the more than 70% or even 95% of gas from the borehole are hydrogen. So this is a good. So they continue exploring the area by using several different methods to confirm the commercial size of the hydrogen field in this area. Okay, and there of course there are several other examples in the world, but this is one example from in Japan, and it's called an Hakuba well. It's an Happo Onsen Obinata no Yu. This drill hole is for the hot spring well. It's an onsen well, and at the same time, well, they have found that these two wells also producing natural hydrogen at the same time with the hot water. So, and we have visited this site last year and found that the dissolved hydrogen in the water is really high. So that means it's promising. So and the hot water and hydrogen is from a particular rock type and fracture zone here. So this means this is only one example in Japan that have confirmed the natural hydrogen production, but there must be much more. Just we don't know where the natural hydrogen is producing, but we need more investigation of where and how the natural hydrogen come from the subsurface. Okay, so well, as I said earlier, and in order to find and explore natural hydrogen from the subsurface, we need to understand the system. So what this system means, and also we need to know the method to explore subsurface. The system, it means it's an idea for finding what you are looking for. So this idea is established in the oil and gas industry. So in order to find a new oil field and gas field in the subsurface, there must be a method. So, and there are some elements and the process to fulfill the condition to form an oil field and gas field. So for example, and for the oil and gas field, it's called the petroleum system. And the elements consist of these 5. So number 1 is the source. Source means is generation. So oil and gas must be produced, must be generated somehow in the subsurface. That is the number 1 thing. The no generation means no potential, right? So the generation must be the number 1. So generation is number 1. And then that generated material will move from the generated area to somewhere. because that is fluid. The fluid can move subsurface. So that is number two things. And number three is the reservoir. Reservoir is a migration pathway and also the reserve itself. So the reservoir is vital. And in order to prevent the seal from the reservoir, it must be a seal layer overlying over the reservoir rock. That is the number four items. And also the trap. Trap is an overall the accumulated hydrocarbon should be trapped there. And then that's why we can find as the hydrocarbon as oil field or gas field. And there's also a condition that is called process. Process means the requirement of the sequence. The trap formation must be first, and then generation, the migration, blah, 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 blah. Where otherwise, the generated and migrated hydrocarbon will go through and disappear to somewhere, and it will not trap. So trap must be first, and then afterward, the generation, and blah, 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 right? So this sequence also the vital condition. So all of these elements and process must be fulfilled to form oil field and gas field. This is called the petroleum system. And for the geothermal energy, it's the same. Of course, it's different conditions. The element will be heat and reservoir and the seal, and the process will be kind of similar, the trap formation first and then heat up. So all of these must be fulfilled, and then we can expect the geothermal energy resources might be there, where otherwise it's nothing, right? So kind of things. So in order to look for natural hydrogen from the subsurface, we need to establish such system for the natural hydrogen, where otherwise we cannot find it. Okay, so its general idea for the natural hydrogen system is something similar to oil and gas, petroleum system. So generation first, and migration, and the trap somewhere in the subsurface. It's basically the same, but the big difference is the source rock is different, and the generation mechanism is different, and the migration and the trap will be maybe a little bit different, because the hydrogen is a smaller molecule. It's easier to leak. So we need to be careful where that rock can be migrated and stored in the subsurface for the natural hydrogen gas field to be established. And also temperature condition is also different. For the natural hydrogen to produce it, the temperature condition seems to be a bit higher. 200 to 300 degrees Celsius will be better. Okay, well, and then this is the science paper and published two years ago. And this suggests the generation can be three types. And one is radiolysis. That is because of the radiation of the uranium and potassium and the and tritium. And these radiation of this material split the water molecule to oxygen and hydrogen. And this is one mechanism. And the second one is it's called serpentinization. This is the alteration of rock that includes the richness of the ions. And that mineral is altered due to the reaction with water, and then that is the original and the iron-rich rock changed into a serpentine and clay minerals, and then during that process, the natural hydrogen will be produced. And that iron-rich rock is common in the deep subsurface, typically from the mantle rock. The mantle rock is an olivine, is a peridotite that include a lot of the such two ions. So that is good. And the number three pattern is deep-seated. Deep-seated means it's from the deep earth interior. So it's typically from mantle. And as I said earlier, the mantle mainly consists of two iron-rich rock, the peridotite and the olivines. So basically number two and number three are the same. And the recent investigations suggest that in the mantle horizon, there's some water there. So that means in the mantle, and the rock and the water can react and may produce hydrogen in such deepness. And that producer hydrogen may come up to the crust and to the surface, and that is regarded as such deep-seated natural hydrogen. Okay, so in order to explore natural hydrogen, the generation is number one thing. Okay, no generation, no resource. So generation, in terms of generation, well, there are four conditions. The rock and water, these are vital, and also temperature to enhance reaction. But the important thing is one more thing is that the fault and fracture. That is also very important because the rock, the mountain rock and such richness of the iron is solid and typically has no porosity, no permeability. So there's no chance of the mineral to react with water. So that's why we need fracture and faults. And a highly fractured rock means that gives a opportunity to react the mineral with water and then produce hydrogen. So that's why the rock must be highly fractured and faulted. So these four elements are vital to generate natural hydrogen. Okay, and another paper suggests different things, but it's almost the same. Well, this paper suggests the abiotic and hydrogen generation is from the radiolysis. It's the same as the previous paper. And the hydrothermal alteration is the same as the serpentinization. And they also suggest the possible source is a volcanic gas. And also the mechanical process of a faulting of rock. It's fine. But in terms of the volume, the such an hydrothermal alteration and typically serpentinization process will be a number one process. And that's what that means. This is still, it's works. So the four items to say explained on one slide ago, it still works. So these are four are still important. Okay, and these are basics. But if you are looking at your area, you need to understand the subsurface of your area, subsurface geology. Then this is around the project in Australia, the York Peninsula area, and they have investigated their area, and they have an idea of the combination of their natural hydrogen in this area. The combination of serpentinization and also the radiolysis and also deep-seated, but the main idea of the natural hydrogen volume of this area may be from serpentinization as well. So this kind of idea must be established by doing some survey and constructed the idea and model, and then they have invested to drill and produce in the next step. And in the geology is complex and it depends on the area. So well, they have simplified such a geology of the area of this one, and this suggests it's a normal faulted, it's less deformed, and the rock react with water. Water is mainly from the surface rainwater. So this is a stable environment. So then the size of the field can be a bigger, and the well drill can be planned there. So they are now doing this. Okay, and of course it depends on the, the complexity of the subsurface geology. It depends on the area. Like here in Japan, the geology is much more complex, and it depends. And there are several different idea of such natural hydrogen system. Its variation locally, and one suggests a possible subduction margin area system, like here in Japan, on your left-hand side. And on your right-hand side, that the top one is something similar to the Australian extensional basin settings as well. And in the lower right is the more compressive, highly deformed area. It also can be a possibility to produce natural hydrogen. So it depends. So, but well, at the same time, we need to investigate in the detail where you are and what kind of tectonic deformation you can expect. And then the local hydrogen system will be valid. Okay, and this is, well, another conceptual model, and this is published this year in Science Advances. And this suggests that the promising area might be a something like this. And this means the mantle rock that include the richness of the two ions is moving upward and located near the shallow or even the surface and react with water. And that is very good situation to produce natural hydrogen. So if we can find this kind of situation in our area, then that will be promising area. Okay, and then this is an example of this kind of promising example. This is from the Pyrenees, the border mountain area between France and Spain, and where it's the former plate collision area. So during that collision process, the mantle rock was exposed on the surface, but that is continuous to the deep. And because of such a heavy deformation, there is a rainwater penetration system in that mountain, and then water go down and react with the mantle rock and then produce natural hydrogen in that area. And in this case, the produced natural hydrogen goes to the French side and also the Spanish side, both. So there are two projects independently in the French side and the Spanish side. And this figure is from the Spanish side, and they are conducting an exploration geophysics survey, and they are planning to drill some holes in such a pore basin area. And another area, another project in the Spanish area on your left-hand side, and they have drilled well already in that area. I'm going to show you the figure later. Okay, and such and highly deformed tectonic belts can be seen many places in the world. So that is the French and Spanish Pyrenees is continuous from the European Alps area. And these red bands are the same situation of such a highly orogenic and highly deformed area. So please look at Japan. That entire Japan is red. So this means the highly altered, deformed, and this can be a promising area. So any places in Japan are very good. And that's why that is encouraging us. And also, well, your area is one of that red area that may have a potential. Okay, well, as I said earlier, this is one example. It is the confirmed natural hydrogen in Japan, the Hakuba Happo and Onsen well. And the location of this well is actually here. Well, this is mid part of Honshu, Japan. This is just next to plate boundary. And the western side of that plate boundary is collided and exposed. So the deeper part of the rock, the former mantle rock, is exposed on the surface, and that is highly fractured. And also this is onsen area, means the heat is high, right? So that fulfills all of the conditions. The iron-rich rock is here, and the water is here because of the highly fractured rock, and also the heat anomaly. So all of these four conditions are here, and that's why this natural hydrogen production from this Hakuba area can be explained that fulfill the basic requirements. Okay, oh yes. So, well, in order to produce natural hydrogen from subsurface, we need some method to explore and produce such materials. And this is a workflow of subsurface energy exploration and production. And this is from the oil and gas. And the same things for the geothermal. And the natural hydrogen gas is the same. So always start from the surface survey, and then do some geophysics to explore subsurface, and then drill to confirm what's there. And if we find the commercial discovery by the well, then we can drill several wells and then produce and sell to the customer. So this is always the same workflow for the subsurface energy resources. Okay, well, this is for the natural hydrogen, the same as oil and gas, the remote sensing survey, the satellite imagery, and we do the same thing and then ground truth to look for the survey, the surface geology, and check the rock, and also the sample collection and analysis. And the center photography is from the Spanish Pyrenees side of this is a surface survey for the natural hydrogen. They are collecting some rock material, and also they are measuring the soil gas of this area. Okay, and next step is exploration of geophysics, like the seismic survey or electric survey and so. So again, this is the same as oil and gas technique. And the seismic profile is from the Spanish side of the Pyrenees. And they have conducted such a seismic survey, and they have found some of the potential area, and they have a drill, and found that the natural hydrogen reservoir just immediately above the basement, and in this case, hydrogen gas is 100%, which is very nice success story. And based on such drill well success, and they have interpret such data again and again, and then the recent interpretation of the seismic profile suggests this natural hydrogen may come from the deep Earth interior from mantle, because the deep fault is existing there. So these faults can be a migration pathway from the mantle to the surface. Okay, and after the geophysical survey, of course, we need to drill well, because we don't know what's there. So after explore and the geophysics, and we just interpret and think about what's there. But the drill well is a direct way to check what's there, because that well, this is expensive nowadays. Just a few thousand meters costs a few millions US$ for just one well. So we need to get enough amount of data set to invest and step forward to the next step. So well, this photography is for the drill well for the natural hydrogen in the Spanish side of the Pyrenees. So they have drilled and found natural gas from that area. Again, the drilling technology the same as oil and gas. So all of these exploration production technology are the same as oil and gas industry. And that's why now oil and gas industry are now really keen on such natural hydrogen exploration and production. So they are doing a massive amount of research and exploration activity, many places in the world. Okay, well, this is the later half of my talk, the Harvard potential in the Kyushu area. And we think that the Kyushu area have a high potential of natural hydrogen because of the rock. Yeah, as I said earlier, there are some key elements, rock fracture and water and temperature. And the Kyushu area has all of these. The Kyushu has, iron richness of a rock. And I'm going to show this in the next slide. And also we have the heat anomaly, high temperature, geothermal gradient in the Kyushu area. And we have a lot of water, like here in today. Just outside, I guess the heavy rain just now. So in Kyushu area, we have a richness of such water resources, which is good. Okay. So yes, our department has started a team of researchers and started the research to examine the potential of natural hydrogen in Kyushu area. Okay, well, these are the typical the iron-rich rocks exposed in Kyushu area. And on your top left is the Shinoguri area in the Fukuoka Prefecture. And on your top right, this is Oita Saganosaki area. And these purple rocks are the serpentine that include richness of the ions. And on your down left, and this is a normal peninsula area, Nagasaki. And you see, again, the purple rock exposed here. And the down right, and there are several different layers of serpentine and ultramafic rocks. This is from the border of Kumamoto and Miyazaki Prefecture area. And Well, I visited these areas in the past few weeks and to check and what kind of rock is exposed here. And this is, yes, and 4 photographies and 3 photographies and from Nagasaki, Nomosaki, and Saganoseki and Oita area, and Yamada village and Kumamoto prefecture area. And all of these has definitely serpentines exposed here. It's good. And when I see a texture, and several differences can be found. So we are going to investigate a little bit more about this in the detail for the next step to investigate more of these areas to assess the potential of Kyushu, of natural hydrogen. And at least when I found that when I visited just a few days ago, the border area of Miyazaki and Kumamoto Peninsula area, the rocks are highly fractured, and something like similar to Pyrenees Mountain. So that is good because the rock is fractured and that have high penetration of water to deep and react out there, and then the hydrogen will migrate toward somewhere nearby. So that is a good story. So that has the potential. Okay, and this is based on the Shagaya-san, the PhD research, and she's just sitting there, and she's going to finish her PhD in the coming weeks. And this is a heat map produced by her PhD project, and that suggests, and of course, Kyushu has a heat anomaly because we have a lot of onsen and geothermal and power plants, and that is good sign. And so, and we need more investigation of these because what we want to know is the deep environment and also the temperature structure of 200 and 300 degrees Celsius of what the appropriate depths, and that should match with the distribution of such iron-rich rocks. So we are going to say proceed this research in the next steps. And this is a preliminary experiment conducted by one of the students of our laboratory. And he have collected some samples from Karatsu area, and that include the basalt and the peridotite. And he have conducted a generation experiment of natural hydrogen from these rock. And experiments suggest, well, of course, the peridotite and has this is a similar to mantle rock that have potential, and also the basaltic rock also has some potential to produce hydrogen. And basaltic rock is common, it's everywhere. It's a huge rock mass. So that means even the ratio will be low, but the rock volume is much high. So in case of the calculation of the reserves of natural hydrogen, these the basaltic rock can be counted. So that we are going to think about this. Okay, and because of such research initiatives, we submitted our proposal to NEDO, the New Energy Development Organization. It's a funding organization in Japan, and they have accepted our application. So, and we have started this research this year, and we set a team of researchers together with the Kyushu Electric Corporation company, and then we are now started working together to research of natural hydrogen in Kyushu area, and also the implementation as well. Okay, and this is a content of our proposal to the NEDO, and we think this proposal, yes, this is the merit of our proposal. The Kyushu is good in terms of the nature, in terms of nature, such richness of the water, which is good for the natural hydrogen, and also for the social the condition as well. In many local government in Kyushu area and has a record of the geothermal utilization, and the Kyushu area has the energy demand from tourist industry and the semiconductors company and so on. So even locally, we have potential customers of such hydrogen and also the energy from such local hydrogen resources. And these are the natural and the social environmentally merit of the Kyushu. and for the Kyushu University and our department research faculty members. And we have, of course, a technical capability because of the accumulated research and achievement in the past years. And for the Kyushu Electric Corporation, they have running the infrastructure operation in the past years, of course. So they have experience of such a practical ability. So these 3 points are the merit to conduct and implement these research activity in Kyushu area. So, well, a little bit in detail, the objective of this research is that the not basically the hydrogen, natural hydrogen and system research, but also we are thinking about the implementation of such resources in Kyushu. And that's why we are working together with Kyushu Electric Corporation people. So these are 3 items. The number 1 is assessment of the production potential of a natural hydrogen system in this area. And number 2, an examination of the natural hydrogen production method, because the method would be different in different area because of the different potential and different rock type, and the production method would be different. So we need to think about what kind of production method would be better for different locations. So we are going to examine of this point as well. And the number 3 point is its implementation to the society. I mean the commercialization. So this is basically a survey of related companies and seek to establish a network of local government and corporations. This is working together with Electric Corporation of Kyushu. Okay, and these are the members of this initiatives. And our department has 7 laboratories, among which 6 members are the members of this research project. And mainly these are young members. So that is good because it's active and energy. So I expect the activity of these members. And Sugases is also a member of this team. And the Kyushu Electric Corporation and also assigned 2 members from the research institute to two members. So that is a combination of research and the company members. Okay, well, this is my last slide. The summary. The natural hydrogen can be a potential environmental friendly energy resource. And that's why many companies and research sectors, governments are working hard in the past just a few years and the coming years as well, and including Japan. Well, Japan has renewed the basic energy plan February this year. And this plan includes natural hydrogen. And this means from this year, the Japanese government is conducting more on the research and production of natural hydrogen in coming years. And that's why we have funded from NEDO just 1 year, but this project will continue in the following years, maybe in a bigger scale. And that's what we are expecting. So this natural hydrogen research will continue for years. Okay, well, in order to conduct such exploration, the natural hydrogen system must be understood. This is number 1 thing. So the system is important. And also within such a system understanding, generation is the number 1 thing. So no generation, no resource. So generation must be the vital things. And the key element seems to be rock, water, fracture, and heat. These 4 elements. These must be fulfilled. And the subsurface energy exploration approach, like oil and gas and geothermal, can be used for the exploration of natural hydrogen exploration and production. And the Kyushu rocks may have some potential. I would say it's a promising potential. So we have started a project funded by the NEDO from this year and the coming years. I think this is the end. Okay, thank you very much.
Thank you very much for a very nice talk, Yamada sensei. Okay, his presentation is now open for discussion. Please provide question or comment, please.
Anything is fine. I love discussion.
Thank you very much for the interesting talk. I find this field is very promising. I a little bit curious about how can people estimate the potential of natural hydrogen. As I understand, the process of creating the natural hydrogen is continuously. So is the potential would be the amount that is accumulated until now, and it's still on the process when we have enough condition about the mineral rock, the water, and the temperature, and some other. So how can you estimate the potential in some particular place?
Okay, yeah, thank you. The estimation of the reserves is still challenge, and there are some publications suggesting say, well, look, in this area had a huge amount of natural hydrogen in the reserves. Fine, but the different thing is that the reaction speed to produce hydrogen, it seems to be quite fast. So that means even we produce some hydrogen from reservoir, that will filled again because of a reaction of the rock and water inside you. So that means it can be renewable. So if that is true, well, it depends on the area. If the reaction is fast enough, then that is filled again. So we can expect a huge amount of natural hydrogen from such reservoir.
Thank you. Do we have a question from online participant?
Oh, yes, it raised hands.
Yes, to Professor Chapman.
Thank you very much for your presentation. I'm very sorry I couldn't be there in person. I find it really interesting that we think that white hydrogen could be $1 per kilogram. This is in line with the the long-term goals of the American government. It's an excellent price point. But I was also delighted to see your map of South Australia that you just showed a minute ago, because that's where I come from. And I noticed that in line with your comment about the necessity for heat, that you also talked about irradiation in terms of providing the impetus for hydrogen generation. And as we know, South Australia is very famous for its uranium reserves. So I'm wondering, do you think this, linking back to the previous question, the high speed or the necessary speed of white hydrogen production could be linked to radioisotopes or, for example, uranium in this case? And should we be focusing on regions with resources such as these?
Yeah, thank you very much for your question. Yes, this area, the York Peninsula area, the natural hydrogen seems to be a combination of different sources. The one is, this is not really a serpentinization area. And in fact, they assume that the source rock is beef. Beef is the bonded iron formation. It's the richness of iron layers and that iron minerals react with water and produce hydrogen from there. So that has a higher potential to produce hydrogen. So that is one thing. And another thing is that you are right that this is uranium area, and the radiolysis to produce natural hydrogen, the speed is much slow. So such radiolysis generated hydrogen may be a kind of, say, of the fossil type of resources. The ones we have extracted, its replacement speed is quite slow, and it will not be renewed.
That's very interesting.
Time scale.
Yeah, that's very interesting, and that maybe links back to your point that rather than radiolysis or this radioactive nature, that heat is more important. And I'm very interested to follow up that and perhaps speak with you more about how we can investigate, thinking back to the previous question again, the speed of generation and the consistency of the source into the future. Thank you very much for your very interesting presentation.
Yes, that is the case. Yes, I agree with you with the point that the temperature is important because of that determines the reaction speed. So that's why we need to investigate such an heat and temperature structure in the subsurface, and need to find a appropriate place to explore and produce hydrogen from the deep subsurface. Yes, true. Thank you very much.
Wonderful. Thank you very much.
Thank you very much, Chapman-sensei. And we also about question from Kurosawa-san from online. Yes, please.
Can you hear me?
Yes.
Okay. Thank you for the very interesting presentation. I'm Atoshi Kurosawa from the Institute of Applied Energy, also the visiting professor of I²CNER. So it is a very good opportunity to know that about the natural hydrogen. So I have a quick question about the cost estimate. So the cost estimate table, as I see, the natural hydrogen cost is $1 per kilogram in the Australian dollar. So it is very cheap in my understanding. So is this definition of the cost is the kind of operation cost? So if you include the finding and exploration cost, the cost could be much higher than that. So what's your guess on that?
Well, it's true. Well, yeah, I agree. Thank you very much for your question. Yeah, then this is a $1 is a quite uncertain value because if the situation allows the natural hydrogen is kind of renewable, then the cost will be quite low. It depends on the amount they can produce. So it's say kind of say yes, you're right that the capex and opex must be considered to calculate the cost in total. So this is kind of say a optimistic value, but it's possibility, and that's why this is attractive, and this is a driving force of the company to proceed for such direction.
Okay, thank you very much. I understand.
Thank you very much for your question, Kurosawa-sensei. And next, no question from online participant? No. Yes, Andri-san.
Thank you very much for the very enlightening presentation, Sensei. So my question is, you mentioned about the concept of the natural hydrogen is almost similar with the conventional one. So my question is, what parameters can determine about how quickly natural hydrogen is recharged? Is it temperature or the depth of the mantle or anything? Thank you.
So your question is what determines the rate of reaction, or?
Yeah. So my question is, what parameters can determine about how quickly the natural hydrogen can be recharged?
Can be recharged. Okay. Yes. Yeah. Okay. Well, the reaction itself is between the rock and water, but the recharge is it's also a matter of migration and also trap, the CO. So it's combination of these. So if a pathway from generation to a trap, and I mean the reserve, is an excellent, then it can be filled quickly through such a migration pathway. But it depends. So it's a matter of things. And then another thing that I didn't explain is that the produced hydrogen will be consumed by other process, by microbial activity, for example. So it's a bit different from other something like an oil and gas. So the hydrogen can be consumed as well. So it's a matter of these combination, and that determines the rate of such replacement of the natural hydrogen from the reservoir. Are you happy?
Thank you very much, Sensei.
Don't hesitate to ask me.
Okay, I will ask you later, maybe in the
Okay.
room.
Thank you. Yes.
Thank you, Sensei.
Okay, thank you. Any question or comment from on-site? Ichiro-sensei.
Thank you very much. Very interesting talk. I just asked you. Me. Thank you very much. I just asked you on some impurity contains in the hydrogen forms. Is there any separation process required for such naturally formed hydrogen? In case of for example, in case of the natural gas, gas is coming from the methane and CO2 and other sulfur.
Yes.
Therefore, I heard that the separation process is quite costly, required. But is this a same with this kind of the naturally formed hydrogen?
Yes. Well, thank you very much. Yes, this is a point that the natural hydrogen may have a lower content in the total gas. So, well, we cannot expect it can be 99.9% of hydrogen in the produced gas. If that happens, then we can use directly this gas to industry purpose. But the hydrogen content may be much lower. So that means that we need to separate the hydrogen. But and we have discussion with the International Hydrogen Research Center here in Kyushu University. And then the one suggestion from the Sasaki sensei is that it may be better to just say burn that gas and use as a heat source. And use that heat for several other purposes. And like the local an electricity or the heat resources for the locals, and that will be a better solution for the locals in case that the hydrogen content is lower than such a commercial purpose, I mean the industry purpose.
Okay, thank you very much.
Thank you.
じゃあ、プラティ先生。
My question was also related to Jai's question. I wanted to find out about the purity of the hydrogen as well, but I think you've answered that. Then the second question is about, I think I saw from your slides that there are already wells in Mali. You showed an example in Mali, but from the topography of the way you explained and the maps that you showed, I don't see any of this map passing around where Mali is. What is the kind of hydrogen that is extracted from Mali?
Okay, yes, Mali is a different mechanism. Mali is not the tectonically deformed area.
Yes.
It's stable. Yes. So okay, well, generation mechanism of Mali is different from Pyrenees or the Japan style. So it's much stable. It is something similar to Australia, for example. And Australian York Peninsula area is not a severely deformed area. So we also expect such the natural hydrogen in a stable area as well. So there are some different patterns to produce
In
hydrogen.
areas where it's not stable, how do you then detect that you have deposits of hydrogen?
Deposit, yes. Well, even such the highly deformed area, and we can find some traps.
Oh.
Yes. Then we can say the drill to such a target, and then possibly find say the natural field of natural field of natural hydrogen from such traps. It's possible. Yes.
Thank you.
Thank you. Thank you for your question.
Thank you. Any other question? Alice, please.
Thank you for lectures. I have two questions. First, what is the geophysical difference between natural hydro case and hydrothermal case in terms of what structure we should search for? And the second
Wait, one by one. one by one. So your first question is what the difference of the geophysics response between geothermal case and what?
one more, please.
Okay, and what's your number one question? Can you say that again, please?
One more.
Yes.
What is the geophysical difference between natural hydrogen case?
No, what hydrogen? Between
natural
hydrogen,
case
yes,
and hydrothermal case.
Hydrothermal case. What do you mean by?
In terms of
hydrogen?
what structure we should search for?
Ah, okay. Well, in terms of a geophysical survey target.
Yes.
All right. Okay. Yeah. The geothermal target would be, yes, yes, the geothermal case is something like this. Yes. And well, yeah. And as far as I understand, the geothermal energy target would be a steam. And that is mainly steam energy for use the electric generation. And for the natural hydrogen, yes, well, that steam could include natural hydrogen as well. Yes, So it can be similar, but a big difference may be the rock, because such geothermal resources doesn't need such iron-rich rocks, but the natural hydrogen definitely need it. So that is the main difference. Okay, and could you give me your second question?
Okay. What is the biggest problem for commercial uses so far?
What is the problem for the commercial uses?
Yes.
Okay, yes. The one biggest thing is the purity of the natural hydrogen, as Ishao sensei suggested. It's true. It may not be high. So that's why we need to think about how do we use such low purity of hydrogen for energy or other industrial purposes. That's the big thing. And also the another thing is that the natural hydrogen may be the style and the amount will be various. Some areas may produce just a small amount. And if the production rate is high, and we could expect huge amount, then it's fine. We can do anything. But if the production rate is low and the amount will be small, then we need to think about how do we use it. So it's something similar to natural energy resources, like the geothermal, low enthalpy geothermal, or the wind, or the sunlight, and it's all depend on the area. So it's something similar to natural energy resources. So we need to think about how do we use it for the locals, especially, because we cannot transport that energy to somewhere because it costs a lot. So it must be consumed by the locals. That is big challenge.
Thank you.
Thank you very much for your
Thank you very much for your
excellent
question.
question.
So, which one? はい、sorry, time is gone now, so we would like to close today's lecture. Please hand over to Professor Yamada again. Thank you very much for your presentation. Thank you.